In the summer of 1687, Isaac Newton published his seminal Principia Mathematica, arguably one of the single most important scientific works ever produced. Within the pages of its 3 volumes, Newton's laid down the foundation of what we know as classical mechanics. And at the heart of this foundation lies Newton's famed laws of motion. Let us briefly consider these laws one at a time. Newton's first law states, any object moving at a constant velocity will remain in motion at a constant velocity, and in a straight line until acted upon by an outside net force. Likewise, an object at rest will remain at rest until acted upon by an outside net force. Let us consider a car. It makes intuitive sense to us that if the car is just sitting there at rest, it will take some force to cause it to move. But what of a car in motion? Newton's law tells us that the car will, without some net force, remain in motion indefinitely. But our experience tells us that if we shift a moving car into neutral, it will decelerate and eventually stop. Does this not contradict Newton's law? In fact, there is an outside net force acting on the car. It is friction. Newton's law may, in fact, better be understood when we think about what is meant by net force. In our moving car, there are 4 major forces to consider. The engine pulling us forward, friction slowing us down, gravity pulling us toward the ground, and the road holding us up. Newton's law means that as long as these forces are balanced, the car will move at a constant rate. Newton's second law states, the net force on an object is proportional to the change in its momentum, or, as it is more commonly stated, force on an object is equivalent to the mass of an object multiplied by its acceleration. It is a simple equation, but it is used extensively. Let us consider a simple problem. How much force must the engine of our car be able to produce in order to accelerate it at 2.5 meters per second squared? This acceleration will take us from 0 to 90 kilometers per hour in about 10 seconds. If we know that the vehicle has a mass of 1,000 kilograms, about that of a Honda Civic, we simply need to multiply. For simplification, we will overlook the extra force we will need to supply to deal with friction. In this case, we need to produce 2,500 newtons of force, or about 562 pounds of force. Newton's third law states, all forces arise in pairs that are of equal magnitude and opposite direction. In the picture, the force of the gas expelled downward by the rocket is reciprocated by a complementary upward force that lifts the rocket. This law also explains why you don't fall through the floor as you stand on it. Gravity pulls you downward. We call this force weight. In order to hold you, the floor must exert an equal and opposite force upward. The force of the floor on you is called the normal force. If this floor was actually the floor of an elevator, and it suddenly pulls you up with increased force, the equal and opposite force you exert on the floor downward also increases. This is why you feel heavier as the elevator accelerates upward. Newton's laws are today so common to our view of the interactions in the world around us that we find it hard to imagine a time when they were not known. They undergird our entire understanding of physics. Newton once said, "If I have seen further, it is by standing on the shoulders of giants." Today, we must acknowledge that our view is from the shoulders of Newton himself.